Okay, here we're going to talk about compound interest. This is a formula for calculating the amount in an account after so many years given a rate and the number of times compounded at that rate. P is the principal amount invested, right there. R is the rate, and it's in decimal format, so if you had like 2%, then your rate would be 0.02 as a decimal, right? You take the decimal spot, move it over 2 spots to the left. N is the number of times compounded in a year. You have it here and here. And then T is the number of years it's compounded. How long did you leave it in the account? So here's an example. If you invested $3,000 initially into account, paying 4.25% compounded quarterly, how much is in the account after 10 years? Well, we invested how much? $3,000. The rate is 4.25%, so 0.0425, right? Move it 1, 2, and I fill in a 0 in front. The number of times it's compounded is quarterly, so quarterly means 4 times a year, right? 4 quarters in a dollar, quarterly 4. That said daily, that's 365, weekly, 52, right? Then the number of years is T, and that's 10. All right, then we put those values into the equation. So we have A equals, that's the amount in the account, 3,000. 1 plus 0.0425 over 4, and this is NT, 4 times 10. Okay, and then basically we put all that in the calculator. You don't want to round off, so you want to try to get this all in the calculator. And where I usually start is this right here, this division. So it's tricky, so I start right there. I do 0.0425 divided by 4, add 1, raised to this power, which is 40, which we can tell, right? And then multiply by 3,000 last. So let me show you how that works. Okay, here's my TI-84, TI-83, same kind of thing. Move it down maybe just a tad. I'm going to start here, the 0.0425, so 0.0425, and then divide it by 4. Okay, now look, I get that decimal. I'm going to leave the whole decimal in there, okay? I'm going to add 1 to it. And then now we want to raise to the power. Don't multiply by 3,000. You're going out of order of operations. The order of operations say do this, then exponent. So raise that. So if I click second answer, and then raise to the 40th power, now I'm going to get a big long decimal, right? And the calculator's rounding it off to there, so I leave it in. And then multiply times 3,000. 4, 5, 7, 8, 50, basically. 4, 5, 7, 8, 50, right? Round up to the nearest cent. The 5 rounds this up to a 10, which rounds that to a 5, right? So 45, 78, 50. Alright, and so here's the steps that I did with the calculator things, but we get the same answer, $4,578.50. Okay, so start in here, work your way up here to the exponent, and multiply last. And these are the exact things that I just did on the calculator. Okay, the natural exponential function is this one right here. It has a e, which is like pi. It's approximated to 2.7182. And it looks like this, e to the x. It's not very much different than the other function, say 2 to the x, or another one, say 3 to the x. It's just the base is changed to the 2.7182 rather than a 2 or a 3. So it's very, very close, as you see on my graph over here. It's the one that goes right along here, right? This is e to the x right in the middle here, but it's closer to 3 than it is 2. Because look it's closer to 3, right? The number's 2.7, so it's closer to 3. It makes sense that the graph should be the same. Alright, now what does that mean? Well, it's a number, and where does it come from? Well, you know, it comes from this different equations, and okay, so it's a number, and let's see where we can see that in our interest formula. So what we do is we say, hey, what happens if we compound the interest continually, like all of the time? Alright, so let's make our compound interest formula nice. Let's make our R is 1, my T is 1, and my P is 1. Okay, and then the number of times compounded, we're going to kind of let that go to infinity, meaning get larger and larger and larger. But it simplifies down to this, right? Now if I make n really, really large, let's look at a graph here. So n becomes really, really large. I change it to an x so I could graph it. 1, 2, 3, 4, 5, 6, 7. This is the graph of that function right here on a graph. And you'll notice that this line is y equals e, so that's 2.718 right there, right? And you'll notice that that goes close to e as we get to infinity. As I put larger numbers for x, this thing goes towards e. It almost is equal e as x gets infinitely large. Okay? So that's what we can say. As you go to compounding like a millionth of a second, meaning continually, not just daily, but all the time, this thing goes towards e. So I can basically create a new formula now, that this is e. So we create this formula here where it compounds continually, and it's p still means the principal value, the rt, so it's a equals p times e to the rt. Right? RT is multiplied together still, but this base now is going to be e because the compounding is continually rather than the base being this big mess. Alright, so let's look at an example where it has compounding continually. Here's an example. If we compound this continually, it says if you invested $3,000 initially, paying the same percentage but compounding continuously now, okay, how much is in the account? Well, this time we have to use this formula. And this is the sequence of events we're going to put in there because our same numbers are true, the 3,000, the 0.0425, and the compounding now is continuously, which just means use that formula, and we have t for 10 years. So remember, this is what it will be written out as. P is 3,000 times e to the rt, 0.0425 times t is 10. Alright, well, this times 10 means get bigger, move to the decimal spot one spot to the right, right there. So what I'm going to put in the calculator is 3,000 times e to the 0.425. You can put it all in as one item, or you can put it in as two separate. I ended up putting it as two separate, but you can put it one line as well. You just got to be very careful because the mistakes are made when you put things all in as one item. So I'm going to do it just like I have it. Second, the ln button, because that's my e to the x right there. And then I have 0.425. I end the parentheses and I hit enter. Okay, because that's just that portion. Then I multiply by 3,000. Oops, 3,000. I get 4,588 and 77. So 4,588.77. Now you'll notice that that's actually more than the other one, right? So because if you compound your interest more, that means you're getting money, you're getting interest all the time, you're getting money and it's compounding on itself, you're going to make more in the long run. So for you as a saving, it's better to compound your interest more, but if you're paying a loan, you want to compound your interest less. Hopefully that helps. You just got to use the right formula in the right situation.